Oh, hey, I didn't see you there. Come on, we're gonna do 4.3 right triangle trigonometry. Okay, so today we're basically looking at a different way to look at the ideas of sine, cosine, tangent, cotangent, secant, all that stuff. Like I mentioned last time, we were looking at it through a coordinate plane and coordinate points. And how cosine related to the x, sine related to the y. This time we're looking at it more the way that you're probably more used to, which is through right triangle trigonometry, the way you would have seen it in geometry. Okay, so we're going to be evaluating trig functions of acute angles, and that's within triangles, using fundamental trig identities, which is just a fancy way of talking about what we already know. And then looking at some vocab for application problems that you're going to be doing. All right. So again, we're going to look at those 6 fundamental trig identities, those trig functions. But this time we're going to be looking at them in the context of this triangle here. So it's always going to be in relation to this guy right here, this angle. It's the belle of the ball, the most important thing in the world. This angle. Everything is related off of this particular point because we have what is opposite to theta, that's over here. We have what is adjacent to theta. Adjacent just means next to. And then the lovely word that we all know, hypotenuse of the triangle. So this is how we determine which side is which, basically. It's all in relation to whatever angle we're using and we're looking at. Okay? So again, we have sine, cosine, tangent, cosecant, secant, and cotangent, and we're looking at theta values that are acute between 0 and 90 within the first quadrant. Now let's look at how these 6 trig functions relate to the opposite, adjacent, and hypotenuse. All right. So basically, what we have going on here is the sine. Let's say that we are talking about this angle. Okay, the sine of this angle will be generated by the ratio of the opposite over the hypotenuse. And I'm not going to write out everything, I'm just going to put an O because that's opposite of theta. This is an A because that is adjacent to theta, next to theta. And this is H because that's the hypotenuse. So the sine of this angle will be opposite over hypotenuse, O over H. The cosine will be adjacent over hypotenuse. The tangent will be opposite over adjacent. Now, it might seem like this is completely different and completely new, but it's really not. If you think about these things in a triangle that just happens to be based within a unit circle, if I can manage to it's kind of a circle.
If this is too boring for you, you can always watch my software update.
My Y coordinate system here. So this is a unit circle. Let's just pretend that it's actually symmetrical and circular. Seem fair? Now let's pretend that the triangle is located within the unit circle. All right, so I'm just going to some dotted lines here. Triangle. And there. Now, isn't it also true that this xy coordinate point would technically be the side length here, x, and the side length here,
I feel like I'd
y.
be appalled to know how many of you are still watching this.
Which, if this is a unit circle and a true unit circle, this hypotenuse is 1. Right? So if I look at the sine of theta being opposite over hypotenuse, the sine is opposite over hypotenuse. The sine is y over 1, or the sine is y. Sine is related to y, that's what we already knew. Also, cosine is adjacent over hypotenuse. Cosine is adjacent over hypotenuse. Cosine is adjacent, that would be the x, over 1. So the cosine is related to x. So these things mean the exact same thing, we're just looking at them in a different context. Okay, we can look at it through the unit circle on a coordinate plane, or we can look at it through relationships of sides of triangles. Let's continua. Use the triangle to find the exact values of the 6 trigonometric functions of theta. Alrighty, seems easy enough, right? Well, the 6 trig functions, okay, let's start with the easy ones. Sine, cosine, and tangent. We know that if we can get those, we can easily get the other ones because it's just reciprocals. Now let's remember what we're supposed to be doing here. Sine is supposed to be opposite over hypotenuse. Cosine is supposed to be adjacent over hypotenuse. And tangent was supposed to be opposite over adjacent. Sine opposite. So from here, opposite is 4. 4 over hypotenuse. I don't have a number there. Well, that's my first snag. 4 over what? How am I supposed to find the hypotenuse of a right triangle given the 2 side lengths? You got an invisible person inside the computer. It is going to be using the Pythagorean theorem. 3 squared plus 4 squared equals c squared, the hypotenuse. So, what is 3 squared? I hope that you all can figure that out. What is 4 squared? I also hope that you all can figure that out. Add the 2 together. We get a fancy, nice number, which happens to come out quite well. And I know that these 2 things are going to have to take the square root of it because this was c squared, and I actually just want c. So c is 5. The hypotenuse is 5. Sine of theta, didn't put my thetas in here, is 4 over 5. Now the cosine should be adjacent over hypotenuse, so that should be 3 over 5. And the tangent should be opposite, 4 over adjacent, 3. 4 over 3. Sweetness! Cool. Now all I gotta do is reciprocal stuff. So, reciprocals down the line, 5 over 4, 5 over 3, 3 over 4. And I have all 6. Seem easy enough? Hopefully it's not too bad. Oh, God, I had so much room there. Alright, so, this next page we're talking about.
This is a good part.
It's some of the very common angular values, 30 degrees, 45 degrees, 60 degrees, their radian counterparts, and then what the sine, cosine, and tangent values of those things are. So this whole column here is sine, this whole column here is cosine, and this whole column here, tangent values. Now, again, I want to try and emphasize that fact that these numbers, these 1/2, square root of 2 over 2, square root of 3 over 2, repeatedly come up and they repeatedly get, passed around in a way between all the different numbers. And I actually want to even try and go a little bit farther and create a rule for how they start to get passed in between each other. So let's take a look and try and find 2 that have the same value. Start with this one, just because it's right here. Sine of 30, or sine of pi over 6, if we're doing radians, is 1/2. Where else do we see 1/2? Boom, right here. So, the sine of a specific angular value and the cosine of a different angular value both have the same number. Is there anything that seems to connect these 2 things together? Because obviously it goes from being sine to cosine, so that's different. 30 to 60, that's also different. But we also know that 30 plus 60 is 90. So these 2 numbers are complements to each other, which I think has to have some significance. So if I have the sine of a particular number, then I also know that the cosine of its complement should be the same. Okay, let's see if that makes sense in different contexts. Let's try something like cosine of 30. If what I said before is true, then if I look at the sine of 60, it should also be square root of 3 over 2, because the sine value of its complement should have the same value. Sine 60 square root of 3 over 2. Would you look at that? On the next slide, we have it written in a more formulaic view. It basically says that the sine of something's complement, remember this 90 minus theta thing is how we find a complement, equals cosine. You have this in your book. You also have these co-function identities in your book as well. So that's something that we can reference over and over until you become more comfortable with which ones relate to each other. The next example we're going to look at is just simply evaluating something using the calculator. So I want to evaluate the cosine of 5 degrees. What is all this gibberish? This says 40 minutes and 12 seconds. All right. If you're not familiar with this notation, I understand. It's more of a navigational tool, latitudes, longitudes. It's simply a way of writing the decimal format of a degree value in a more simplified version. If you think about even just telling time or hours, days, these things are split into minutes and seconds. We don't say that it's 3.25 o'clock or anything like that. We use minutes and seconds. So it's simply just another way of writing it. So the first thing we have to do is convert this a little bit. I know that I have 5 degrees, but this 40 minutes and 12 seconds part is a bit unnerving. So why don't I go ahead and change that. It's pretty much 5 degrees plus this fraction of a degree. 40 and then out of, we know that there's 60 minutes, so 40 out of 60 degrees plus another 12 out of 3600 because they are 12 seconds in an hour. Fantastic. Now, these are degree signs, by the way. If I were to add all these things up, 5.67 degrees, that would be my decimal approximation of these degrees, minutes, and seconds. So this conversion, kind of unnecessary to do. It's more time consuming than it's really worth. Remind me when we're in class, there are some buttons on your calculator that'll do it for you. Okay? No need for you to have to bother yourself with it. As long as you understand the conversion, this is minutes, so I'm putting it out of 60 because there's 60 minutes. And then 12 seconds, I'm putting it out of 3,600 because there's that many seconds. So now that we have this, evaluating this on a calculator is quite simple, and you've probably already all done it. There is a cosine button. It automatically comes in with that first parenthesis already filled out. You type in 5.67. No need to put a degree symbol. All you have to do is make sure that in your mode you are in degrees. Otherwise, we'll get a very different answer if you're looking at 5.67 radians. Make sure you put that end parenthesis in there, and then hit enter. What you should get out for this is somewhere around 0.995. If you do not, again, check your mode. Make sure that you have that in degrees because we're working in degrees right now. All right, so what this gives you, it tells you basically, is that you are looking at a degree value. Say this is your initial degree value that's very, very small, which makes sense, right? This is only 5.67 degrees. So the cosine value, the x, is almost all the way at 1, 0.995. Trigonometric identities. We already know all of this. This isn't new. I know looking at it, it might seem a little bit freakish, but none of this is new. We know that the sine is the reciprocal of cosecant. We know that cosecant is the reciprocal of sine. This is just writing it out mathematically. We know that cosine is the reciprocal of secant. Secant is the reciprocal of cosine. Simple. Tangent reciprocal of cotangent. Cotangent reciprocal of tangent. Now, the quotient identities. We also know that tangent is sine over cosine, correct? Now, because cotangent is supposed to be the reciprocal, stands to reason that if tangent is sine over cosine, I should just be able to flip it, cosine over sine. It's the same thing for cotangent. So from here up, that should have been new. Good. Not a problem. I already knew it. Maybe just a little bit of notation. Now the bottom, that's a little bit different. Now, the way that I like to look at this is my triangle. inscribed within the unit circle, right? Now, we had talked about it before and said that this over here was essentially, because this is an xy, that this is my x, this is my y, right? The sides of the triangle basically are x distance and y distance. Now we know that x relates to the cosine. We know that y relates to the sine. Now how do I find the hypotenuse? If I didn't know that this was a unit circle, how would I find the hypotenuse given these two sides? Pythagorean theorem, right? So even knowing that this is a unit circle, I could say one of the sides, which I'm representing as cosine, squared, plus the other side, which I'm representing as sine, squared, equals whatever the hypotenuse is. I know this is a unit circle, so it's 1, right? Or if I wanted to use x and y, x squared plus y squared equals 1. Very, very interesting. Now this right here is the first one there, Pythagorean identity. Right? And it's simply the idea of using the Pythagorean theorem within the context of cosine and sine to find the hypotenuse. There's, again, nothing particularly new there beside notation. These other two that are below it are simply derived from this equation by doing one single operation. And I would like to challenge you to figure out what one operation in order to get this. Also, what one operation is done to this, which yields this. One operation for each. Now we want to try and apply these trigonometric identities. Let's try and see what they look like when they're actually being used, and hopefully if there's any misconceptions about them, we can solve it up in this example. I have some theta value that has an acute angle, and the cosine of this particular acute theta value is 0.8. I want to figure out what is the sine and what is the tangent using these identities that I just talked about. Alright, well that seems impossible. Let's look back. Is there any equation that I have there that somehow relates cosine to sine or tangent? Cosine relates to secant, secant relates to cosine, so those doesn't really help. Sine relates to cosecant, cosecant relates to sine, that doesn't help. No. So none of these things at the top really seem to help. I need something that relates sine and cosine and tangent. So maybe something like this. Maybe something like this. But that leaves me with one value that I know, two unknowns. So that's not really going to work. I wonder if the Pythagorean identities can help me out. Even though they don't really seem like the nicest of sorts, I think that they might work. Sine squared plus cosine squared equals 1. Let's see, what can I plug in here? Sine squared plus, and I know that the cosine is 0.8, so 0.8 squared equals 1. Now this brings up an important point. When I say sine squared or cosine squared, I do not mean that the theta value is squared. I mean that the cosine value is squared, that the sine value is squared. Alright, so that's why I put 0.8. That's the value of the cosine of this angle that's being squared. Alrighty, so let's see if we can move on from here. How do I move on from here? I got 0.8, I could square that if I'd like to, I guess. Or you can move it over to the other side. Let's do that. Sine squared equals 1 minus 0.8 squared. Okay. Well, this is going to be 0.64, so sine squared equals 1 minus 0.64 is 0.36. Cool. Alright, this is actually looking like it's going to be a little bit easier than I thought. If I have something that's squared on one side, I want to take the square root, so I can just get the regular sine straight out, equals, and the square root of 0.36. Don't get confused by the decimals or anything. Basically the square root of 36, but 0.6. Boom. Almost done. Just got to do part B. But Part B is going to be so much simpler because I know cosine is 0.8. I know sine is 0.6. What trig identity relates sine, cosine, and tangent? Tangent of theta equals sine over cosine, which means 0.6 over 0.8. Boom. Look how simple that is. Since I'm super smart, I know that that's about 0.75. And that's my tangent value. I have successfully found the sine and the tangent using only trigonometric identities. And it really wasn't even that bad. All that I had to do was understand 1, 2 different relationships between values. Oh, jeez, I always forget that I have more space. Now, when we do some application problems, we're generally going to be solving right triangles. Okay, whether those right triangles are in a forest or on the side of a building or relating bearings or something, it's generally right triangles. We'll get into more complicated ones later. And there is some vocabulary that's going to be used in those that I just want to leave you with. Angle of elevation and angle of depression. Now these things might seem intuitive and they might seem obvious, but I'd be remiss if I did not talk about it. We're basically looking at this horizontal as if it's that initial point. An angle of elevation goes from the horizontal in a counterclockwise motion upward. It's like a positive angle. An angle of depression goes downward. Right? So if you're talking about like a pool that you're making and it slowly descends to the deep end, there would be an angle of depression there. If you're talking about flying a kite up in the air, the angle of elevation of the kite. Okay? Just some brief vocabulary there. Do the exercises that are assigned, and good luck. Peace!